Hello everyone, Mr. Tomashik here. In this video, I want to take a few minutes to do a quick review of the 4 states of matter: solid, liquid, gas, and plasma. Now, you probably studied this a little bit already in 9th grade, so hopefully it's mostly review. Probably the easiest example to talk about would be water. Right here I have some ice, which is just the solid form of water. And if you look at it really close, you can't really see the individual water molecules there. But ice is solid water. And if I let it all melt, now I have liquid water. It's still water in every respect, but you can't see these tiny little particles that make it up. And the difference between solid, liquid, and gases is what the molecules are doing inside there. Now, if I were to say take this water and just set it on the table and let it sit for a few days, all these water molecules would just evaporate and disappear. And in a gas, you can't really see the molecules at all. You can't see anything. It looks like it disappears like that. Now, even the ancient Greeks had a little bit of a notion about everything existing as little tiny particles. And in fact, the word atom comes from the Greeks, meaning cannot divide. When we study atoms later, we will talk about that a little bit more there in detail. All right. Now, as far as the gas goes, here I have a flask, and most people would look at that and go, it's empty. There's nothing in there. But in fact, there are gas molecules inside of there, and I could put my hand over the top and contain that gas. And once contained, then I could heat it up or cool it down or even squish it. Something we'll also talk about a little bit later too as well. So the difference between solid, liquids, and gas is that the motion of the molecules. All right, let's take a look at a simulation we're going to use in the lab here shortly. In this simulation, it helps us visualize, see what we can't normally see. Right now we're looking at a solid, and you can see the little particles moving around, and they just kind of wiggle back and forth, but they generally stay in the same position and don't really spread out at all. So solids can maintain their shape all by themselves. If we look at a liquid, is different from a solid in that the molecules can move around and change positions, and the liquid itself can spread out and take the shape of the container. Here we can see there's a few molecules that just fly right off the surface and turn into a gas and fly all over the place. But the main difference is that in a liquid, the particles are just moving a little bit faster, and they can change shape and spread out, still interacting with each other quite a bit, but moving a little bit faster. Now, in a gas, the molecules are quite far apart, and they just fly all over the place, bouncing off the bottom, the top, the sides, etc. And they would fly right out of the container if there was no lid on the top of it. And if you heat them up, they start moving faster and faster in there as well. And they do interact with each other a little bit, but they're so far apart that that interaction is much less than it is in a solid or liquid as well. Now, in this simulation, we can put different kinds of gases in there, and you'll see when we do that. For example, argon, oxygen, water, etc. Air is a mixture of different kinds of gases. So what is air made of? Air is a mixture which is mostly nitrogen. About 78% of air is made out of nitrogen molecules. About 21% of it is oxygen, and that leaves about 1% for everything else. Now, when you breathe in, most of what you breathe in is nitrogen molecules, which are N2 nitrogen molecules, and then also oxygen, and that's the stuff that your body needs when you breathe. The nitrogen just goes in and comes right back out. Nothing happens to it. The oxygen interacts with your lungs and comes back out as carbon dioxide. Now, the 1% is everything else. That would include carbon dioxide, helium, water vapor, and the percentages, of course, depend on the air. This is sort of an average. If you went out and scooped up some air outside, it would probably be close to these percentages here. Air inside of buildings might be a little bit different because buildings contain people, and people breathe and breathe out carbon dioxide. So the level of oxygen would probably be less, and the level of carbon dioxide, the other stuff, might be greater. All right, so this is sort of an average. Air is a mixture of nitrogen, oxygen, and small amounts of other things. In fire, fire is a plasma. Now, this fourth state of matter, what we call plasma, is kind of rare on the Earth. And plasma, for the most part, is fire. All right, is fire. All right, most of you are familiar with fire, like in a candle. All right, if we had a candle, the candle is made out of solid, and some of it might melt and make a little puddle of liquid, and then the liquid could vaporize and turn into gas after a chemical reaction is happening. Things like water molecules or carbon dioxide will come floating out of this. But at the point where the flame is, this is a plasma. It's kind of like a gas that's at very high temperature, and it's ionized, and somewhat rare on the Earth. But we're familiar with fire. We see it all over the place, and that's kind of our fourth state of matter. Very similar to a gas, except the fact that it's a higher temperature and is ionized usually, so can be influenced by magnetic fields and things like this. Now, the sun is made mainly of a plasma, and the sun is much, much more massive than the Earth. So the most common state of matter in the universe would then be a plasma, because the solid liquids and gases like we have on the Earth is actually quite rare in the universe. So most of the stuff that makes up the universe is a plasma, and plasmas are where nuclear fusion happens, something we'll talk about a little bit further down the road as well. Now, some of you may be familiar with this little device here, a plasma globe. Let's take a look at one of those. This is a plasma globe. All right, and you can touch it, and it's kind of like got little streams of lightning. Now, what is this? Inside of here is a gas under very low pressure, and the electricity is creating ionization of that gas, and that ionization is creating those little streams of plasma like that. Now, since there's very little gas inside there, any heat that's actually made here does not conduct outward very well at all, though you can feel a little bit of heat when you touch it. And plasma globes kind of got some weird effects, and these things you can buy on Amazon like that, about $20 or $30 depending upon how big they are. A plasma globe, just another example of a plasma. Take a look at this diagram. This is an illustration of the sun over here on the side. The sun, and then the sun every once in a while might put out what we call a solar flare, just sort of a big burst of flame that comes flying out. And when that happens, it sends its plasma out into space, and it might even fly toward the Earth. And fortunately for us, though, this plasma, being charged particles, can be influenced by Earth's magnetic field. And Earth's magnetic field sort of shields us from these charged particles that come flying toward the Earth, which is good because that could be kind of dangerous for us. But do notice that some of these particles do make their way into the Earth's atmosphere way up on the North Pole and the South Pole. And when they do, they will interact with the atmosphere. And some of you may have actually seen the effects of that. These charged particles from the sun. Here we're looking at some pictures of the northern lights. And some of you may have seen this before. If you go far north, like in northern Minnesota or Canada or Alaska, you can see the lights much better. Because of the Earth's magnetic field, we only see these when we are close to the North Pole or the South Pole. In the northern hemisphere, we call it the northern lights. In the southern hemisphere, the southern lights, or aurora borealis, or aurora australis. Now, what is this from? When those charged particles from the sun come flying toward the Earth and get in the magnetic field and enter at the North Pole, they interact with the gases that make up the atmosphere, and it makes those gases glow. And that's what you're looking at, the northern lights. The reason that you see colors sometimes is an artifact of the different particles or gases that make up the atmosphere on that particular day. So when you see the northern lights, know that it is an artifact of something that happened in the sun a day or so ago. And we can predict when good northern lights are going to happen by watching what's going on with the sun. Okay, let's take a moment to do a little review of changes of states of matter. That is, we could go from, say, a solid to a liquid, and we call that process melting. Or we could go from a liquid to a solid, and that process is called freezing. So you can take liquid water and freeze it, you can take solid water and melt it, and in either case, energy is transferred. When you put heat into it, we call that an endothermic process. So melting is an endothermic process. We put heat into the solid and it turns into a liquid. If we take heat out of the solid, we call that an exothermic, like the heat is going to the exterior, out of the stuff. And the process of freezing would be considered exothermic. Now, going from a liquid to a gas is also endothermic. If we put heat into a liquid, we can vaporize it or turn it into a gas. And that process is called evaporation. And going the other direction is called condensation. And in the fall time, like today, this morning, there was a lot of fog outside, and that's just gas that's vapor in the atmosphere turning into little tiny droplets of water liquid, and we call it fog. If the droplets get big enough, then they fall down as raindrops and hit the ground as well. All right. The third process could happen if we have solids turning into a gas and skipping that liquid stage. We call that sublimation. And ice can actually sublime. All right, rather than melting, it just vaporizes, turns directly into a gas. And in your freezer, that happens a lot. If you had a tray of ice cubes, say, sitting in the freezer, they may just disappear, but have never melted. And that's called sublimation. That too is endothermic. Heat goes in, and you change from a solid to a gas. Going the other direction, having gases turn into solids is called deposition. It's kind of the opposite of sublimation. All right. In either case, either heat goes in or heat comes out. Heat goes in or heat comes out. We call that endo or exothermic. And that's a term or terms that we're going to use quite a bit later too as well when we talk about chemical reactions. And chemical reactions can be either endo or exothermic as well, but that'll be a little bit further down the road for us. The main topic for this unit is called the kinetic molecular theory, or sometimes we just say KMT for short. And that basically is just this. Even though you can't see that stuff is made out of tiny, tiny little particles, the kinetic molecular theory tells us that these particles are always moving around, whether it's a solid, liquid, or a gas. In a gas, however, they move around quite rapidly and longer distances and bounce off all kinds of stuff and do things like create pressure, which we'll talk about a little bit later. All right, in this kinetic theory that all stuff is made out of little particles that are moving around in sort of random motions, and account for things like pressure, temperature, and that sort of business too as well. Right? In this theory, we believe that these collisions with like the walls of the container or the ceiling or the floor or something like that, they bounce off of stuff and don't really lose energy in the process. All right, they're like perfectly elastic, we say, which is not entirely true, but as a gas is sort of having its molecules just flying around, their speed is a factor of their temperature, and they just continuously bounce off and hit the walls and ceiling and stuff like that too as well. All right. In this theory, when we start to throw in things like pressure and temperature and stuff, we're going to assume that the volume of the particles themselves are really kind of insignificant compared to the volume of the whole thing, especially in the case of gases here. All right, so kinetic molecular theory, it's just sort of a concept, an idea that all things, solid, liquid, or gas, are made up of little particles that are always moving. And if they get hot, they move faster. If they get cold, they move slower. If they stop, well, they really couldn't get any colder. That's what we call absolute zero, which we'll get to a little bit down the road too as well. So this current unit we're going to call KMT and gas laws. And we'll talk more about gases and the concepts of pressure and temperature and volume and how those things are all related to each other in like Boyle's Law, Charles' Law, Gay-Lussac, and others as well. But we'll talk about that a little bit later. All right, so that's kind of our quick little review. You maybe didn't call it kinetic molecular theory back in 9th grade, but I'm pretty sure that you had studied solid, liquids, and gases and plasma a little bit and got an idea what the difference of those things are. All right, thanks for watching.